Okay, and so Tatiana will speak about deep neural networks for inverse problems with pseudo-differential operators and application to limited angle tomography. So over to you, Tatiana.
Thank you, and thank you for giving me the opportunity to talk today about this recent work we did. So, well, you read already the title, but I can go on by introducing the collaborators. So this is a work that we did while I was still at the University of Helsinki with my supervisor, Samuli, Siltanen, and Lassas, and then with Luca Ratti, who is now at the Machine Learning Journal Center in Italy, but was at the time also in Finland, and then with Mathilde Galinier, who is now also, she finished her PhD, but back then she was spending a brief period with us in Helsinki, and their supervisor in Modena, Marco Prato.
Okay, Tatiana, your slides actually aren't sharing.
Ooh.
I can still only see the title screen.
Okay, let's do this way.
Oh, no, it's...
Okay, but let's do the. Yes. Does it show?
Yes.
Okay. Okay, well, you had a bit of spoiler, but so as the title was saying, the idea and the motivation comes from an application in limited angle tomography, and there are many that one can think of. One probably very famous at this point is breast imaging with tomosynthesis, and another one which we're probably very familiar with up until some time ago, it's airport luggage scanning control. And one that is very close to the group in Helsinki is the dental imaging panoramic. So in all these cases, one has to deal not only with a tomographic problem, but also with having only a limited angle for the scanning procedure. And well, if there is, for those of you who are not familiar with tomographic imaging, in a nutshell, and to give the idea, what we want to do in this case is that we have an object. It can be a luggage, like for the luggage control scanning, or it can be like the human body, or it can be a part of the human body, or it can be any other object. For instance, here I chose the picture of a walnut. And for the sake of this talk, we think of a two-dimensional object, so a slice of the entire object. But in general, like the devices work for 3D imaging. And the forward problem in that case, so the tomographic imaging gives us measured data, which look like superimpression of sinusoidal curves and these are usually called, for this reason, sinogram. So we, in case of the forward problem, we know the physical quantity and we compute the measurements, and we're giving what we call the sinogram. What we deal with in this talk is instead the inverse problem, where after we're given the measurements and we want to recover the object, or better, the X-ray attenuation of the object. And the measurements are in general noisy, and this complicates the matter. From a mathematical perspective, what we're dealing with, and what usually at least the first generation of CT scanners did, were sampling the radon transform. So in general, there were like an array of X-ray sources, and these were emitting X-rays, and at the other side of the object, we would find a detector that was measuring the incoming photons. And then the array would rotate a bit. Usually it's not that neat. The rotation is like a tiny bit, part of an angle even, and then the arrays are sent through the object again. And once we collect the whole thing around, then we have our sinogram. Mathematically, this is modeled through the radon transform, which you can see written on the slide. And the solution to invert the radon transform has actually been known for a while, over a century, and it's in a famous paper from Joan Radon. And the discrete contrast to the implementation of this formula then is summarized by a very well-known algorithm, which still to date is widely employed in CT scanners, and it's called filter-based projections. So while this is still one of the main algorithms in nowadays devices, there are some issues with it. One is instability under perturbation of the data. So in general, we are not, the detector will not collect RU perfectly, but there will be some noise on it, which we model with this plus epsilon. And the instability gets worse and worse when the data are scarcely sampled. This means when they are sparse. So for instance, we sample only here and there around the object, or when they are limited, like in the case of the application we have in mind for this talk. So what does really happen mathematically when we have limited angle tomography? So the first thing is that we are basically limiting the source or the array of sources in a limited arc. So it doesn't go all the way around the body. And so this is usually said that we have a limited wedge for the active angles. This means that the parameter for the angles is limited into a subinterval minus capital gamma for us. And we denote the limited angle radon transform by R gamma. So what happens, some observation in nutshell, is that usually in this case, we can preserve uniqueness provided that we have infinitely many angles. And this, of course, is never the case in a discrete world. So already here we encounter some problems. But then the stability gets even worse when the angle range is reduced, because we start to have noise, we start to lose data, and the problem is then said to be severely ill-posed, not just mildly ill-posed like classical tomography. And to understand what this means in practice, let's consider this slice is a slice of a human abdomen. And here we are assuming to have still full angles, and we use FPP, so filter-based projection, to reconstruct. So this image is pretty good, but we have all the data and a small amount of noise. When we start reducing the visible angles, so gamma, we start to see that we are losing information in the reconstruction if we use the filter-based projection to do the reconstruction. And the more the arc is limited, the worse the reconstruction is, and we can see a consistent pattern where striking artifacts starts to appear, and the information is lost, basically. So we cannot recover the parts that are not measured, basically. And yeah, so if you even reduce it more, like here, the information about the object is basically non-existent, and I think no one would guess what we are looking at here if we wouldn't have seen the full scan image at the beginning. This has been well studied, especially within the theory of macrolocal analysis. And in a series of papers, I think one of the most famous one is by Todd Quinto in 1993, where he characterized what are the parts that we can predict to reconstruct and those that are impossible to recover. And basically, this is understood in terms of the wavefront set of the singularities, and we know that we can expect to see the singularities that are tangent to the measurements lines. Okay, so this is the motivation, the setup where we start from. And before presenting a tentative solution that we provided in this work, I want to present the key ingredients that we're gonna need to carry on. So basically, this talk balances is an interplay of different areas. One I presented it already is tomographic inverse problems, but then also sparsity regularization, multidimensional representation system, and neural networks, unrolled schemes, unrolled neural networks come into play. Let's see how. So we saw what in practice means to have a tomographic inverse problems. One way to formalize this is that we can set it up as a linear inverse problem where we are given some measurements M, they are noisy, there is the noise epsilon and bounded by some delta, and we wish to recover U dagger, which is the true solution, so the ground truth. And one way to do it, especially when we are in a regime of scarce data or limited data, like in this case, is to use techniques called sparse regularization. So basically what we do is that we recast the problem as a minimization one, where we have two terms. One, which is in general an L2 term, is the so-called data mismatch term. So is this term here with R gamma and W star W minus M. And then there is a second term, which is lambda L1 norm of a certain W, which is the so-called regularization term, and lambda is the regularization parameter. Here we are minimizing over W, which for the sake of this talk is a certain transformation of the U that we want to reconstruct. So in particular for us, this is going to be an orthonormal wavelet transform, but there is this different other formulation. One can use different orthonormal bases, and one in general could, in principle, regularize directly on U and then add, for instance, non-negativity constraints. But this is what is called a synthesis formulation associated to our discrete inverse problem. Okay, so what we do with this is that basically we are enforcing sparsity in the wavelet coefficient. I will explain a bit in details what are the wavelet coefficient in the next slide, but for the sake of understanding this formula here, bear with me a moment. And enforcing sparsity would be that the solution of this problem usually favors a vector W that has as much as possible 0 elements in it. So it's a relaxation of a nil zero sparsity problem. What are wavelets? Well, if you never heard the word wavelets, the idea is that for instance, is that it's a way to break down a signal into a different basis, into building, and each building block is represent a coefficient according to an element of the basis you are considering. So what we do is that we have a certain function, which is usually called mother wavelet. Many exist. The most famous one and the easiest one is the R wavelet basis, but also Dobeschi wavelets are very famous, and different mother wavelets usually exhibit different properties that can lead to orthogonal system or bi-orthogonal system, and that can be compactly supported or band limited. In the case of R wavelet, for instance, this is gonna yield us leave us with an orthonormal basis, and it's compactly supported. And once we have our mother wavelet, what we do is that we parameterize with two parameters. J is called the scale parameter, and K is the location parameter. And J allows that the mother wavelet has a smaller support or a larger one. We are, of course, interested in the smaller support, and then K is the offset across the plane, and this is how the family is generated. So in practice, what does it mean when we have, for instance, the two-dimensional image in the walnut is that we, after we apply the wavelet transform, depending on the parameter j, so how much scale we have, we end up with an image of the same size, and the image is virtually divided in different levels and in different blocks called subbands, which identify different details in the image, which are usually vertical, horizontal details, and then what we will denote with F between brackets is the low pass filter, so the information about the lower frequencies, okay? So when we infer sparsity with respect to a wavelet basis, we are basically getting rid of the possible noise that there is in the image and forcing the edges to be really present, as you see, like in this image of the walnut, where we try to capture the edges of the walnut. Okay. Once we put this together, one very famous algorithm to solve the formulation I had in a couple of slides back is the iterative soft thresholding introduced by Dobeshi, De Vries, and De Mol in 2004. And what it does is that it iteratively computes a solution by applying the soft thresholding operator to the previous iteration minus two terms. The middle one you see here is basically a representation of the normal operator associated with the Radon transform, limited Radon transform in the wavelet basis. And then there is a so-called bias term here, which is the one that contains the measurements M. And what it does, the soft thresholding operator, is that it pushes to zero the smaller coefficient, okay? Here, capital L is a step size, which is related to the Lipschitz constants of the problem. What it has been proven in the paper is that once you fix a maximum number of iteration capital N, then we can, the W star, so the adjoint of the wavelet transform times the approximation computed at the capital N iteration is an approximation of the solution map of our inverse problem. Okay. So the last building block we need before actually getting into the content of the talk is that from this formulation of ISTA, one can move towards neural network and unroll the iteration of ISTA and consider them as layers of a neural network. So our nonlinear activation function will be the soft thresholding operator, but then we define the weight coefficient on main parameters of the problem as the element of the capital K. So this representation of the normal operator of the Radon transform in the wavelet basis. And then, as I said before, B is the bias vector, which we keep fixed. And the learning happens only on the coefficient contained in the kernel K. And one can also decide to learn other parameters like the regularization parameter lambda or the step size L, and then other problems like the number of iteration or layers in this case can be a hyperparameter of the problem. This has been done in the literature. I think the paper from Gregor and LeCun where they introduced learned is from 2010, and then there were a couple of more recent papers, ISTA.NET from 2018 and FBComNet from 2017, which are similar in spirit to this one. So they enroll the iterations and they are recurrent neural networks. Maybe FBComNet, it's actually not enrolled, it's a convolutional neural network. So if we now define a map f theta, where theta are the parameters that we want to learn, which associate M to, again, the adjoint of the wavelet transform times the approximation we get at the final layer, then there is always a choice of the parameter theta, and it's the one where we keep fixed also the kernel parameters capital K, such that the f of theta 0. So for this choice of the parameter, we basically recover the usual classical ISTA iteration that we had in the previous slide. Okay, starting from this, which was a very lengthy introduction to present you with all the ingredients we need. Well, the question is, well, we have a neural network. Can we make this into a convolutional one? So is it possible to move towards having a convolutional neural network? And the answer is actually yes. And how we do this, it's pretty nasty. So I included the formulas for completeness, and so if you want to look at it in details, but actually I'm just gonna explain them in spirit now and then show you pictures that hopefully are gonna clarify the situation a bit more. But now imagine that you are again working in the wavelet basis. So again, you are seeing like this K that was here before. Now is like the representation in the wavelet basis of the normal operator of the limited angle radon transform. Since we are in the wavelet base, we have different sub blocks. They are the subbands, and we denote each block capital K going from J to J prime and from T to T prime. But this, the most important one is the J index that tells us from which scale we start to which one we want to arrive. Basically, this identifies a subband in the wavelet decomposition, and depending on where we wanna move between subbands, we have three different cases, okay? And what we see from here is that to apply each subband to a stack of wavelet coefficient Wj, we need to perform three operations, which are discrete convolutions, downsampling, here denoted with D, and upsampling, here denoted with U. And the K tilde are the filters. So the definition of the filters is quite mystical, but don't worry, I'll explain you how to derive them. So the good news is that basically, starting from the expression of the normal operator of the radon limited angle radon transform in the wavelet basis, we can exactly rewrite it as a convolutional layer, so as a combination of three operations. How do we do this in practice is represented here. So in a nutshell, what we do is that we start with our image. We are always working in the wavelet domain. So our image is subdivided in different subbands. Here I show three, but they can be two, could be five, depending on the size of your image. We decompose it. We imagine to have the different subbands collected, and then we perform the discrete convolution. I'll explain in details in a moment how we do this. And once the discrete convolution has been done, we go back to putting together all the different results we gathered, and then we sum it all together to again get the final wavelet image. Okay. So how do we do this in practice? Concrete example. Let's suppose we have an image of size 2 to the 6th, and we consider three scales. So we have three different levels of subbands of size 2 to the 5th, 2 to the 4th, and 2 to the 3rd. Okay, and now what we need to do is that for each one of these subbands, we need to perform the convolutions with certain prescribed filters, where the filters have been prescribed by the nasty formula we had a couple of slides back. So how do we do this? Let's suppose we choose a subband of dimension 2 to the 4th, but then this argument stands for each one of the ones you see here. You just have to adjust it to the different cases of J prime. So what we do is that depending on the size of arrival, so depending on J prime, we divide in three cases. The cases are three because we decided to have three scales. So if we have at our final dimension is, for instance, lower, then we first convolve with the filters, and then we downsample as much as needed. So if the dimension is just from 4 to 3, then we downsample once. If we need to go to 2 step downs, then we downsample twice. If the dimension remains the same, we just convolve with the filters. And if we need to go up in the dimension, we first upsample and then perform the convolution. And again, we upsample as much as needed, depending on how many scales we decided to have. In this way, at the end, we're going to have another series of subbands so that you can reassemble your wavelet transform. And we have as many as the subband we started with. So we get, for each small subband, we get, let's say, one green image. And if we have at the beginning like 10 subbands, when we get 10 green images. Before moving to the last step, I didn't tell you how to derive the filters. So the filters are derived like this. We start in the wavelet domain, and we basically have an image which is all 0 except from 1 pixel in the center, which is activated, and it's equal to 1. And we decide to activate the diagonal subbands of the coarser resolution here, but then we need to repeat this process for all the subbands there. Then we apply the wavelet inverse transform or adjoint. I mean, in our case, it's orthonormal, so it doesn't matter. And we basically, by project, we go back to the image domain. And here we apply the normal operator of the radon transform. And as I showed at the beginning, this is gonna provide an image which has the striking artifacts that are typical of the limited angle transform, okay? Because we first obtain the sinogram and then we try to reconstruct with the unfiltered back projection, and that is what we get. And then we go, again, in the wavelet domain. And so this image is split according to its details in the different subbands. And each one of these subbands makes the filters. So in the end, here again, we chose to have three scales. We could have more or less, and we get 10 filters. So it is clear that if I start with 3 scales, so 10 different subbands, then in the end, I end up with 100 filters, okay, which are needed to perform the operations here. So now you also understand why we have filters of various dimensions. Okay, and all this is actually precisely prescribed by this formula that was written here. So you see that depending on the case, we either downsample and then convolve, we either just convolve when j is equal to j prime, or we first convolve, we first upsample and then convolve. And the filters definition is below. Okay, so this is the operations. And as I said before, when we get many of these green images, so wavelet image, we sum it all together, and that's the output of the network. So one problem is that each layer is an application of many convolutional filters. In the case where we had 3, like the one I exposed to you, this means 100 basically. And then we not only have to do all these operations, then we also need to upscale and downscale. And the filters are generally of different dimensions and can be very, very large, because if we start with a 512 by 512 image and we choose 3 scales, then the smallest subband is 128 by 128, which means we would convolve with something that large in principle. But we can decide for how the filters are obtained. We can always decide to threshold, so consider only the innermost part, so pick the center of these filters according to a certain threshold tau. So just notice that now we are doing a thresholding, which is not the soft thresholding, it's just this infinity norm thresholding. So it's a box in the innermost part of the filters. And one can prove that if we discard the outer, let's say, frame of the filters, you're not losing much. It amounts to having a perturbed iteration of ISTA, for which convergence can still be proven, and the bound is at the bottom of the slide. So we will see later on that we chose a tau, and then the filters are either tau by tau, tau times tau, or smaller. just before moving to presenting the network itself, I told all the story, assuming that we are dealing with a limited angle radon transform, but actually in practice we could replace it with an operator A acting between Hilbert spaces, satisfying some assumptions. I think the most restrictive ones in the one is requiring that A is a convolutional kernel operator. So actually we're asking that it has a Calderon-Zygmunt kernel. So it has discontinuities at most along some lines, but for instance, the requirements on the wavelet basis is basically nothing, and our wavelet will do, and actually we use that wavelet in our experiments. Okay, so going back to the general part, so we can now define the convolutional neural network. We call it pseudonet because we can show that it learns a pseudo-differential operator. I'll explain more on this later, but let's just see how it works. So we have operators capital Kn, which are implemented according to the architecture I introduced. So it's this combination of upsampling, downsampling, and discrete convolution coming straight out of the theory, so rewriting the normal operator in the wavelet basis. Then we consider only the central part, tau times tau of the filters, and the rest it's fixed. And so it's the same as the ISTA filters, basically. And then we learn additional parameters, for instance, the regularization parameter of the step size and the number of iteration and tau we treat as hyperparameters. And the interpretation here is that we are learning a correction on the normal operator A star A. So basically, the convolutional neural network substitute A star A with an operator whose kernel we can split in two parts. K0 is the kernel of A star A, and it's fixed. It's kept like this. Oh, sorry. Okay. And then the other part, K1N, is concentrated on the diagonal, and it's the pseudo-differential part. So we propose two architectures where they are equivalent, but provide very different efficiency compared to the implementation. So the first one is the closest one to this interpretation I gave. It's called the filter-based, because after we compute the convolutional filters, we do exactly this splitting into K0, which is the outer part of the filters, and then we take out the center, so the tau times tau part, and those become the trainable part. So basically this lambda tau z is the one which we initialize with the innermost part of the filters, and then where the learning happens, and we leave the outer part untouched wherever there is no learning. And so we basically compute the filters. So this is done offline, and then we use the external frame non-trained, and then we learn the center of the filters. This makes sense because the information is really concentrated in the inner part from a macrolocal perspective. Also more on this later. The other one is that, as I told you already a few times, we still, yes, we can compute the filters offline and store only store the outer parts and then learn the innermost part, but this is very time consuming, and we end up with doing a lot of convolutions with the outer part, with the big filters of the outer part. So what we can do instead is directly don't compute the filters, but have it as a on-the-fly operator way. So we apply the operator A transpose A, and you can use your favorite implementation of the limited angle radon transform. And then on top of that, we learn a center with the proposed architecture and the trainable filters. Okay, so this way we don't have we do this step a bit faster, and that's the reason why we called it operator-based, and the flow of the network is below. Okay, so they are equivalent from a theoretical perspective, but the operator-based is way more efficient than the filter-based. I won't spend much on these. Basically, under minor assumption and in the case of Gaussian noise and doing the necessary restriction in non-infinite dimensional spaces, you can prove convergence to the network. I think probably a bit more interesting than this is why this network can outperform ISTA and why are we actually learning a correction which is a pseudo-differential operator. So I try to give an idea more to avoid to leave you like in the uncertainty and try to convince you, but these are arguments from Macrolocal analysis. So my understanding is this is not really my piece of cake. So apologies if I can convince you fully. So what we do when we apply Psi DONet is that whenever we are learning a correction, because we know that the worst we can do is recover the normal ISTA iteration for the choice of theta equal to that theta 0 we had at the beginning, we can definitely improve on numerical errors, mitigate the modeling errors that there is in representing A itself, and provide a representation of A as the normal operator in a slightly different basis. But the strong part is that it works as a macrolocal regularizer. So imagine now that instead of learning a different capital lambda at every iteration, as it actually happens, we just learn always the same capital lambda. This is equivalent to solving standard ISTA for sparsity-promoting regularization of a different problem, one which is A star A plus lambda U equals to A star M. And lambda is a learned pseudo-differential operator. So here, for those of you who are a bit familiar maybe with Tikhonov regularization, writing this should ring a bell, even though it's not the same. But if instead of having capital lambda, you would have, for instance, scalar, so alpha times the identity, then that would resemble Tikhonov regularization. So in spirit, you can think of, like, you can get the idea from that. But here it's a bit more refined situation. So what we would do now is that if we want U, then we have to invert A star A plus capital lambda. And to do this, we can apply the numerous series expansion and truncate it at a certain order. And this basically leaves us with a sum of terms of A star A times the inverse of the pseudo-differential operator capital lambda plus a regularizing reminder here, okay? And what happens now is that since lambda is an invertible pseudo-differential operator, what happens in practice is that in general, its inverse has a regularizing or smoothing effect. And this is good for us because if A star A is, for instance, a pseudo-differential operator, like it is the case with the classical Radon transform, then once we have A star A lambda to the -1, we still have a pseudo-differential operator. And what happens is that we can reduce the intensity of the singularities, okay? So we cannot get rid of the singularities, but the intensity is reduced. If instead A star A is a Fourier integral operator, and this is actually the case of limited angle Radon transform, then lambda cannot prevent singularities to move around. So the streaking artifacts that is typical when we apply filter back projection, but it can reduce its intensity. So even if they move around, they are not as intense as you would expect. Okay, so in practice, what we can do is avoid that in solving in our problem, we blow up the singularities that are inevitably present in there, okay? Okay, so after this intense 2 slides of macrolocal analysis, hoping convincing you that this should work, let's move to the numerical part. So now, again, we come back to having the limited angle Radon transform. It has been proven that R star gamma, R gamma is convolutional with a Calderon-Sigmund kernel that you see written down here. In particular, this key of gamma is the indicator function of the visible wedge. So it's basically, it says to you like which angle are visible. And As I said already a moment ago, this is no longer a pseudo-differential operator, but is in general generalized Fourier integral operator, but it still can benefit from learning a pseudo-differential correction for the motivation I just gave. So it makes sense to apply this whole thing to it. We start discretizing anything. In practice, there are many different ways to implement the radon transform. We used ODL based on the Astra toolbox, and then we used PyWT for Python's wavelet transform, and we used 10 different subbands, which means 3 scales. I present results from 2 different data sets. One is pretty classic, is the data set of the ellipses, size 128 times 128, and a missing wedge of 60 degrees in parallel beam geometry. And then another data set which was made available after the Code Sprint Challenge of last year. It's a data set with apple slices with different kinds of defects, external or internal defects in the slices of the apples. And the original data set has size quite large, almost 1,000. So we needed to resimulate the data. So it's like the images are like the images comes from a real apple, but the data are simulated again with the same projector we used for the ellipses. So these are also resized to 128 times 128, and the missing wedge is again 60 degrees. The results that I present here are from the implementation we have in TensorFlow 1 with using Adam. And we used 120 layers or iteration of unrolled iteration of ISTA, and we fixed the thresholding for the filters to 32. And we add 40 different sets of trainable parameters. Okay, so 3 epochs for the ellipses and 2 for the apples. Okay, so some results. For the ellipses, this is one case, and you see basically in the first row the ground truth and the standard classical techniques. First filter a back projection and then standard ISTA. And you see that the images are a bit like you would expect. FPP exhibit like the striking artifacts. ISTA does a bit better, but it's still like kind of smoothed. The intensity is, if you look especially at the part that should be yellow, is really not there. And then below you see the 2 different implementations of pseudonet, the filter-based and the operator-based. And again, these are equivalent, so it's no surprise that they provide pretty much the same result. The important thing is that the operator-based is way more efficient. Okay, and you see that the reconstruction is better in suppressing especially the artifacts. So it's this idea that we can smooth out the intensities of the singularities so that they become less present in the reconstruction. And for the sake of this talk, we had no aim of recovering the missing part or whatever, but just to improve in a center, really the center of the of our filters. Okay, and we have similar result for the apple slices, and you can see that FPP and ISTA provide pretty much the same situation where the artifacts are really suppressed, and then our network does a fairly good job. It's very blocky, but this is because this is our wavelet, so I actually would expect as much. I would be surprised not to be that blocky. Okay, so some conclusions. The idea is that pseudonet is a network that learns pseudo-differential operators. Is interesting because theoretically can be deduced from some computations, so it has it's easy to interpret in that sense. We provided the convergence analysis to see that it outperforms the iterative soft thresholding algorithm, and we provided 2 different implementations, and the main message is that this comes from an interplay between different areas of mathematics. So as you can see, we need a regularization theory of inverse problems, but also harmonic analysis with wavelets, macrolocal analysis to understand what's going on, and in the end, machine learning. The main reference where you're going to find all the details and more proof is written there. And if you want to play around with the codes, they are available on GitHub. And there are 2 different implementations, one in TensorFlow, the one we used here, and then one in PyTorch. And we are still continuing to work in this direction. So we're working on the generalization problem, so proving the convergence of the training network. And as you've seen, there is quite a lot that can be done on moving towards real data. So working on bigger images, this current implementation has a horribly slow training on the 512 times 512 images. It goes from like a few hours that now requires to almost 2 weeks, so quite a lot. And then if we want to go back to the initial slide and actually work with some application like breast imaging, then we should definitely have a smaller visible wedge and scarce angle in the visible wedge. And a lot of work can be done also on the loss function, on the hyperparameter optimization. And on the side, one might be even interested in extending to other inverse problem and try how it works, for instance, with synthetic aperture radars and in general on geodesic X-ray transforms, since the theory covers it. And with this, I finished. And if you have questions, I'm happy to answer them.
Thank you very much, Tatiana. That's a great talk. I'm just going to stop the